In today's discussion, we're going to be talking about work. With this discussion, everything has already been filled out, so hopefully that doesn't upset you too much, but again, it's just to save time by having the problem solved already, and I'll just kind of talk about how I got to the answer that I did. Starting off initially, we so far in this class have basically hit on a few topics, or broad themes, or frameworks as I like to call them. The first framework that we talked about was something called kinematics, which I have written down over here. And if you think about back to the kinematic equations and dealing with that kind of stuff, basically that was to solve for like time or displacement or velocity or all that good junk. Then we started to look into Newton's laws, and in particular, we focused in on Newton's second law, which says F net equals ma. And we've done some problems with that, where we had forces and free body diagrams and all that good stuff. The last framework that we're going to talk about in this whole overriding topic of what's called mechanics is energy. Right? And energy turns out to be an interesting way to look at things in terms of does an object gain energy, lose energy, or just keep the same energy. So that's what this discussion is talking about, is kind of getting into this idea of energy. And work is a form of energy. In physics, the idea of work is the process of moving an object by applying a force. Okay, so the object has to be moved by applying a force. And so some examples of work would be like pushing a snowblower, pulling a sled, moving books from the floor to a shelf, all that good stuff. Right? Mathematically, you can express work by saying work equals force times distance. Force times distance, and work is a scalar quantity. So the good news is you don't have to worry about up, down, left, right, or any of that kind of stuff. It just has a magnitude. The units of work are the joule. All right, the joule, which is represented with a J. Also, a joule is a Newton meter. So if you think back to torque, work and torque are very similar in that they both have Newton meter as the unit, or also known as the joule. One big thing that's really important for this formula right here, work equals force times distance, is you can't just use any old force in this equation. Only the force that's applied in the object's direction of displacement actually counts towards doing work. Okay, so for instance, if this object or this box is pushed this direction, I'll call this the displacement, with a force in the same direction, these two guys are working together, no pun intended, to create work, or do work, I should say. Whereas if you have just a box at rest, or let's not even do that, let's say I am pushing on a wall, okay? I'm applying some force to the wall, but the wall is not moving any distance, right? So even though I push on a wall and I become exhausted, no work was done because there was no displacement. On the flip side, let's say you have a box sitting on the ground. Here's the force of gravity, here's the normal force, and let's say the box is just sliding across like some ice for some reason, or it was just sliding across the ice. Notice this force here, and here is the displacement of this box. They are perpendicular to each other. So in theory, this normal force and the force of gravity does no work on the box. Okay, so only the force in the direction of the displacement counts, and we'll do some examples of that in just a second. Let's keep on moving down. So since only the force in the direction of the displacement counts, we need to add in this cosine theta piece, the cosine theta piece. And you may say to yourself, why? Well, let's say I'm pulling on a box, and let's say I'm pulling on a box with a force of 500 newtons at an angle of 30 degrees above the horizontal. Okay? If we think back to when we had to break forces into components, we know that this force, there is a x component and there is a y component. Which component, and let me draw on one more thing before I ask this question. Let's put that the box moves this direction. Okay? The question becomes, which component will be responsible or is in line with the displacement, the x or the y component? Well, the answer is only the x component is in line with this displacement, and so only that component of this 500 Newton force can be taken into account in the work equation. And if you think back to your trig functions, you have to take the cosine of this angle to figure out the x component, and that's why that's there. If you really struggle with trig, which hopefully that's not the case, but if you really are struggling with it, the formula basically takes care of it for you, so you don't really even need to think about it per se, but that's why that's there. And if the force and the displacement are completely parallel with each other, So let's say it looks like this: force, displacement. If they're completely parallel with each other, the angle between these two arrows would be 0 degrees. If you ask yourself, what is the cosine of 0 degrees? The answer is 1. Okay, and that's why sometimes we don't even care about this term because they're both parallel with each other. The force and displacement are parallel with each other, and we automatically know 1 times anything is just itself. And actually, my first example problem is going to be exactly this scenario. So let's take a look at it. It says an appliance salesman pushes a refrigerator 2 meters across the floor by applying a force of 200 newtons. Find the work done. Okay, so if you want, feel free to draw a picture, but here's this refrigerator. A force is being applied to it by the salesman, and it moves in the same direction as the force. Notice these two are parallel with each other, so theta equals 0 degrees in this work equals force times distance times the cosine of whatever the theta is. So cosine of 0 is 1, so we basically can kind of ignore this term. It says the force that the salesman applies is 200 newtons times the distance of 2 meters. 200 times 2 would be 400 joules of work was done. Okay, so that's basically it. That's how you calculate the amount of work that was done. Let's do some more example problems. A friend's car is stuck on the ice. You push down the car to provide more friction for the tires by way of increasing the normal force, allowing the car's tires to propel it forward 5 meters onto less slippery ground. How much work did you do? Well, this one kind of involves a little bit of a picture here. I'm going to really exaggerate the car's bumper, and I'm not a real good artist, but we'll say here's the car's bumper right here. If your friend pushes down this direction with some force, okay, and the car moves this direction, notice these two guys here, they make an angle of 90 degrees. That is theta. The angle between the force and the displacement is theta. So if you take the cosine of 90 degrees, and feel free to do this in your calculator and check it out, the cosine of 90 degrees is 0. I can put any force I want in on this times any displacement I want, but if it's times 0, guess what the work done is? 0. Okay? And so there actually was no work done by your friend because there was no displacement in the vertical direction. All right, so that's kind of an example of when work might not be done. Okay, let's take a look at another example. You push a crate up a ramp with a force of 10 newtons. Despite your pushing, however, the crate slides down the ramp a distance of 4 meters. How much work did you do? Okay, I'm just going to draw a real quick ramp here. Here's a box. You're pushing with some force of 10 newtons. Okay, so we know that. Force equals 10 newtons. And despite your pushing, however, the crate slides down the ramp a distance of 4 meters. So it slides down the ramp this way, a distance of 4 meters. That's bad 4. It's supposed to be a 4, though. How much work did you do? Well, the formula for work is force times distance times the cosine of theta. The force is 10 newtons, the displacement is 4 meters, and you'll notice I have a cosine of 180. How come? Well, if you measure this angle between the force and the distance, or displacement if you will, that's 180 degrees. If you take the cosine of 180, that gives you a -1. So -1 times any positive numbers is going to give you a negative answer, and so you can actually have negative work. It's -40 joules. What that basically means is this box lost 40 joules of energy, okay, as it slid down the ramp. Okay, so you can have negative work. Don't think that that's a wrong answer. That is very possible if the force and the displacement are in opposite directions. Typically, the number one thing that's going to provide negative work is friction, because friction is always going to oppose your motion. So it's going to be always in the opposite direction of the displacement, and so that almost always will provide negative work. So keep that in mind. Question: how much work is done in lifting an 8-kilogram box from the floor to a height of 2 meters above the ground? Well, the first thing is that the box has a mass of 8 kilograms, right? So I'm kind of wondering what the force of gravity is upon that box. So I do that right here. I take 8 times 9.8, because remember weight equals m times g. So 8 times 9.8 equals 78.4 newtons. Okay, so that's what that number is. I'm just finding out what is the force of gravity. 78.4 newtons. I have to overcome that force of gravity basically to move this box upwards. And so to figure out how much work it's going to take to do that, I'm going to take 78.4 newtons, that's my force, times a displacement of 2 meters. 78.4 times displacement of 2 meters would equal 156.8 joules of work. You may say, well, where's the cosine piece? Well, if you just even draw a quick picture, the force and the displacement are in the same direction, and the angle between them is 0 degrees. So I kind of got lazy here and I didn't write cosine of 0. But if you take the cosine of 0, it'd just be multiplying it by 1, and then you'd still get the same answer. Okay, so that's why it's not there. This last problem, I can't ignore the angle here, and I already see a major typo that I did here. I put the wrong work formula, so I'm really sorry. That's supposed to say cosine of theta. Please ignore that. Barry and Sydney pull a 30-kilogram wagon with a force of 500 newtons, a distance of 20 meters. The force acts at an angle of 30 degrees to the horizontal. Calculate the work done. All right, if I just draw a real quick picture here, here's the force of 500 newtons. The angle here is 30 degrees, and the displacement is this direction here to the right. All right? I can't just use this 500 Newton force straight away. I have to account for this angle here, and the formula does it for me. So basically, I'm just going to plug in work equals force times distance times the cosine of theta. The force is 500 newtons times a displacement of 20 meters times the cosine of 30. All right, so it's just basically a calculator work at this point if you just recognize or don't forget to put cosine of 30 in your equation. So you take 500 times 20 times the cosine of 30. If you do that math problem, you should get 8,660 joules of work. Hopefully that helps a little bit with work and makes life a little easier. If you have any questions or concerns, feel free to email me or see me in class. I will see you guys later.